Hello, everyone. Welcome back to the CMS 436 Mechanics of Composites. Today, we're going to talk about the macromechanics of composites on the ultimate strengths of unidirectional lamina and also the compression of a unidirectional lamina and the failure mode. So first of all, I want to show you guys how to express those ultimate strengths of a unidirectional lamina. Since for those unidirectional lamina, we have different properties, physical properties in the transverse direction and the axial direction, right? So for the longitudinal direction, we express everything with the subscription 1, and for the transverse direction, we have this subscription 2, right? So in the longitudinal direction, we have both tensile strength, ultimate tensile strength, right, with the T expressed here, and ultimate compressive strength with the C expressed here. And same case for the transverse direction. And we also have the in-plane shell strength, which is expressed with a tau 1,2 ultimate strength. Okay, so now we assume the fiber and matrix are all isotropic and homogeneous and linearly elastic until failure. So that's the assumption for this model. And the failure strain for the matrix is higher than the fiber, which is the case for most of the polymer matrix composites, right? For example, for the glass fiber reinforced epoxy composite, the glass fiber fails at a strain around 3 to 5%, while for the matrix material epoxy fails at a strains around 9 to 10%, right? So usually for the polymer matrix composite, the fiber, the maximum strain for the fiber is smaller than the maximum strain for the composite, for the matrix. So we show this fiber, the ultimate strength for the fiber expressed with in this way, and the Young's modulus of fiber ultimate tensile strength of matrix and Young's modulus of the matrix here. If we see this chart to compare with the fiber, the mechanical strength fiber of fiber composite and matrix, right? We'll see that for the x-axis, we have the strain, y-axis is the stress, right? So this is the stress strain curve of the unidirectional composite under the uniaxial tensile load along the fibers, right? So this longitudinal direction. And you'll see that for the maximum strain that can be applied to the composite and fiber is the same, right? So because if the fiber, for this composite, if the fiber fail, that means the composite is fail, right? So that's why maximum strain for the fiber and the composite is the same as the maximum strain that is, or the ultimate strain of the fiber. While for the matrix, they have the much larger ultimate strain for the matrix, right? That is usually true for most of the composites, especially for polymer matrix composites. And what about the stress, right? What about the stress for the composite fiber and the strain and the matrix? So we know that for the stress of the composite can be calculated based on the stress on the fiber and stress on the matrix. So if you use the rule mixture, you can see the stress, ultimate stress of the composite should stay in between the ultimate stress of the fiber and also the stress of the matrix at this point, right? So you should use the stress at this point to calculate so this is the stress M that should be used to calculate this stress of the composite, right? Ultimate stress of the composite. So you can calculate this based on rule of mixture. And we know that the ultimate stress of the fiber is much higher than the matrix, right? And therefore you can get this composite, you can increase the ultimate strength of the composite compared to the matrix. All right, so for the ultimate failure strain of the fiber, you can calculate the ultimate strain of the fiber based on the ultimate stress of the fiber and the Young's modulus of the fiber. So this is really straightforward, right? We know strain equals to stress over Young's modulus. That is also true for the ultimate, to calculate the ultimate strain based on the ultimate stress. So that's the same for the matrix, right? You calculate the ultimate strain of the matrix based on this relation. So because the fiber carries most of the load in polymeric matrix composite, so usually the fiber fails first, right? And usually this one is smaller than this one, right? So the maximum allowed strain is actually for the composite is the ultimate strain for the fiber, right? If you apply the load for so if this is a composite, right, unidirectional fiber reinforced composite, and we apply force in the longitudinal direction, we all know they share the same strain, right? They share the same strain for the composite, fiber, and the matrix. Right? So those strain should be the same if this composite is withstand this kind of loading. So that means the maximum allowed load strain will be the smallest strain. Okay, so based on the rule of mixture, we know that for the ultimate strength of the composite can be calculated by the strain, the stress applied to the fiber and the stress applied to the matrix, right? So we know the composite in the unidirectional direction, right? That will be equals to fiber stress on the fiber times volume fraction of the fiber plus strain of the matrix times volume fraction of the matrix, right? So this is the rule of mixture. And for the ultimate strength, we have this as the ultimate strength of the composite, right? So for the fiber, the fiber will withstand the ultimate stress, right? Because fiber will fail at that time. So you have the fiber with ultimate strength with times fiber volume fraction. And here, for the matrix, for the stress that is applied to the matrix is actually calculated based on the strain and the Young's modulus of the matrix, because matrix does not fail at that point, right? So this is a strain that is applied to the matrix. So the stress applied to the matrix will be equal to strain times Young's modulus of the matrix, right? So this will be the stress of the matrix. And if there's no void, the volume fraction of the matrix will be 1 minus VF, right? So this is true to calculate the ultimate strength of the composite in the longitudinal direction, right? Tensile strength. All right, so now we want to ask a question. Once the fibers have broken, can the composite take more load? That means we want to know if the composite will have a completely fail if the fibers has broken in middle, right? So we don't want the composite completely fail in both of the cases, right? So then we have to calculate the stress that the matrix can take without the fiber. So that's the case when you only have in this matrix, in this composite, right? You will have broken fibers inside, right? So that means for the stress that the matrix take alone will be ultimate stress of the matrix times volume fraction of the matrix, right? Because the fiber doesn't take any stress anymore. So that's the maximum stress that this failed composite can take, right? So let's compare with this stress, right? Compare this stress with the stress before the fiber fails, right? The stress before fiber fails, that is the ultimate, that is expressed by the previous equation, right? So this is the ultimate stress of the composite before fiber fails. So we have to compare with those two. So this is the case after fiber fails. This is the case before the fiber fails, right? So we want to we want this one larger than the fiber fail before the fiber fails. Therefore, you can calculate the volume fraction of the fiber. The minimum volume fraction of the fiber can be expressed by the stress, the ultimate stress of the matrix, ultimate stress of fiber, Young's modulus of matrix and the fiber, right? Is that right? So the key is that if you want to find out if the composite can take more load after fibers is broken, you have to derive it based on this equation, right? This relation. So this relation means the fiber can take more load, right? This is higher ultimate strength. After the fiber, this is the ultimate strength before the fiber is broken. So therefore, you can find out the minimum volume fraction of the fiber. So if the volume fraction of the fiber is less than this value, right? It's less than this value. That means the composite will not fail, will not completely fail after the fibers are broken. Right? Does that make sense? Okay, so if you add fibers to the matrix, the composite may have lowered the ultimate strength, ultimate tensile strength than the matrix. What does that mean? So if you add in, let's go back to this figure, right? So we calculated, we know this ultimate strength of the composite, right, will be calculated based on this ultimate strength of the fiber and also the strength of the matrix at this time, right? So, and this is calculated based on volume fraction of fiber times volume fraction of the matrix. If you have a really small volume fraction of the fiber, you may have this composite line here, right? This may be your stress strain curve for new composite, right? Composite 2. So this may happen, right? And that therefore the ultimate strength of the fiber of the composite is actually lower than the ultimate strength of the matrix. That may happen. So we don't want that. We want to, the goal is to increase your ultimate strength of the composite compared to the ultimate strength of your matrix. So let's go back. So there's a critical volume fraction of the fiber that has to be reached to effectively increase your ultimate strength of the composite. So if we compare this ultimate strength of the matrix and the ultimate strength of the composite, right? If this ultimate strength of the fiber is larger than the composite, that is bad. So in this way, we can calculate this critical fiber volume fraction based on this equation. Is that right? If you want to have the composite, if you want the ultimate strength of the composite is higher than ultimate strength of the matrix, you want your volume fraction of the fiber larger than the critical volume fraction of fiber. Is that right? Okay. So now let's look at the example. First of all, I want to show you guys the typical properties of fibers. The graphite, glass, and aramid fiber. You can find out the axial modules. You have the transverse modules. You have the Boston ratio, transverse Boston ratio, shell modules in the axial direction, coefficient of thermal expansion in both directions, right? Tensile strength, in axial direction, compressive strength in axial direction, tensile strength, compressive strength in the transverse direction, shear strength, and specific gravity. So it's, most of these physical properties of fibers, right? And this is the typical properties of matrices, epoxy, aluminum, and polyamide. So now we also have these physical properties of this matrix. So based on these physical properties of matrix and fiber, we want to solve this example. Okay, let's see what is this question. So we want to find out the ultimate tensile strength for glass epoxy lamina with a 70% fiber volume fraction. Use the properties for glass and epoxy from the previous tables, and find the minimum and critical fiber volume fractions. Okay, so see, this is the drawing is not great. So we have this epoxy matrix, right, with glass fibers inside, and glass fibers have 70% volume fraction. Okay, and then we know the ultimate strength. We want to find out the ultimate strength of the composite, right? Ultimate strength of the composite. Of course, in both transverse direction and longitudinal direction, right? For 1, 2. You can try to solve it by yourself. All right, to save some time, let me continue on how to calculate this. Okay, so first of all, you want to calculate the ultimate strain of the fiber and ultimate strain of the matrix to see which one is larger. Okay, because we know the Young's modulus of the fiber, Young's modulus of the matrix, ultimate stress of the fiber and the matrix. Then you can find out the ultimate strain of the fiber, ultimate strain of the matrix, right? So you see this ultimate strain of the fiber is lower than ultimate strain of the matrix. That means the fiber will fail first, right? So that means the ultimate strain of the composite will be equal to the ultimate strain of the fiber, right? So that's the ultimate strain of the composite. So you use the ultimate strain of the composite to calculate the ultimate tensile strength. So the tensile strength, ultimate tensile strength will be equal to the ultimate stress of the fiber, because fiber will fail first, right? At that time, fiber will fail, and times the volume fraction of the fiber and the ultimate the stress that is applied to the matrix at that time has to be calculated based on the strain applied to the matrix, right? Because the strain are the same. Right? You use the strain and the Young's modulus of the matrix, that's the stress applied to the matrix. Right? So in this way, you can calculate the ultimate longitudinal tensile strength. Okay, so to calculate the minimum fiber volume fraction, we simply apply this equation. We simply use this equation, or you just use the relation. You use that relation between the ultimate strength of the failed composite and the ultimate strength of the composite, right? To see before the fiber fails, to see which one to see which one is larger, right? So based on this equation, we find out the minimum volume fraction of the fiber is around 0.66422. So that means if the volume fraction of the fiber is less than this value, right, the matrix can take more loading after all fibers break. So that means the volume fraction of fiber has to be extremely small if you want the matrix take more loading after all fibers break. Right. So to calculate the critical fiber volume fraction, use this equation we just derived, and you can find out the volume fraction is 0.6732%. It's also really low. So what does it mean? That means if the fiber volume fraction was less than this value, the composite longitudinal tensile strength will be less than that of the matrix. So here, because of the ultimate strength of the fiber is way larger than ultimate strength of the matrix. So if you have the volume fraction of the fiber larger than this value, that means the composite tensile strength is larger than that of the matrix. And if you want to use the experiment to check the ultimate strength, you can use this tensile with a mechanical tester to pull this dot bone shape of the composite. Right? So in this way, you can directly measure. You can use the strain gauge to measure the strain on the composite, right, on this sample. And this stress can be measured by this machine. Right? So in that way, you can measure the ultimate stress of the composite in the longitudinal direction, right? So this is the typical stress strain curve of the laminate under longitudinal tensile load. This is the experimental data. Okay, so in this way, you can easily find out the Young's modulus, right? Because Young's modulus is actually the slope of this curve, right? This linear curve, and the ultimate stress is the ultimate. You will have the maximum stress shown here, right? And this is also the maximum strain. It should be a straight line. Right. So to measure them experimentally is really easy to get a stress strain curve. So for the longitudinal compressive strength, usually the composite, the unidirectional reinforced composite, you don't want those composites to withstand compressive strength, right? But some cases, they have to withstand the compressive strength. Right? For example, if you have if you have this composite, right? This lamina, and you have this fiber, reinforced fiber, unidirectional fiber in this way, and sometimes you may want to have a hole inside, right? You may have a hole inside, and you may want to use a pin to hold this hole, right? You may want to use a pin to put inside. Right, to hold this piece, and this pin will compress with one side, right? And therefore, at this area, right? At this area, this composite will withstand compressive loading rather than tensile loading. Okay, so that's why we want to look at this longitudinal compressive strength. So typically, you have three types of failure mode. First type is the fracture of matrix or the fiber matrix bond due to the tensile strain in the matrix and the bond area. Okay, so in this way, if you compress this, if you put compression force in this direction, right, you will, based on the Boston effect, you have this tensile deformation, this deformation in this way, right? So that therefore you will have the tensile stress in the transverse direction. Therefore, you may have the fracture of the matrix and the fiber and matrix bond, right? Also, the second mode is the macro buckling of the fibers in shell or extensional mode. So that means, so if you know, if this is a slender bar, right? If this is the slender bar, and you apply force in this way, the slender bar may have a buckling, right? May have the buckling failure. So that's the same for the fibers. So they may have the small the macro buckling, right? In this way. And also you may have the shell failure of the fiber. So if the fiber is not strong enough, you may have the shell load, because you apply in this way, you may have the shell load in this direction. So the failure may be cut off. So that's another failure mode. Okay, so we have a schematic on the mode of failure on the compression. So this is the A and B are the macro buckling failure mode. If you have the fiber, it depends on the density, the volume fraction of the fiber. If you have a low volume fraction of the fiber, you may have this extensional mode. If you have a high volume fraction of the fiber, this macro buckling may happen in the shell mode. Okay? And this is the transverse tensile failure of the matrix. So you have this fraction or cracking in the matrix. And shell failure of the fiber happens because of the shell loading of the applied to the fiber. Okay, so that's the 3 or 4 failure modes on the compression. Okay, so assuming you have one applying the longitudinal compressive strength, you have this ply applied with the longitudinal compressive strength. So the strain by the compressive stress will be calculated by the compressive stress and the Young's modules of the material, right? So that's the deformation. That's the compressive strain in one direction, right? That's the longitudinal direction. So you can calculate the strain in the transverse direction based on the Boltzmann ratio. So we know the Boltzmann ratio 1, 2 equals to minus strain in the two direction over strain in the one direction, right? So the strain in the two direction, which is the transverse direction, will be equals to minus strain in the one direction times Boltzmann ratio 1, 2, right? To make it easier, we have this, we consider all the strain stress as positive number, okay? So the transverse strain will be tensile, right? This is a tensile strain. And that means this value should be positive. You can calculate it based on the stress that is applied to the composite. Right? And therefore, you can use this strain to you can base on the maximum strain failure theory. That means you don't want this strain in the two direction exceeding the strain, the ultimate strain in the two direction, right? So by using that maximum strain, you can calculate the stress that can apply in the one direction, right? So let me draw this. So this is a unidirectional composite, right? So this is one direction. This is the one direction, right? And this is two direction. If you apply the compressive force here in the one direction, you will have the deformation in two direction, right? So if you have a maximum strain in the two direction, or the ultimate strain in the two direction, you don't want to exceed that, right? If that's the failure mode, which means the matrix or the matrix and fiber bonding fail, right? So let's see if this is the ultimate tensile strain of the matrix, right? So you don't want to exceed that. So by using this strain, you can calculate the maximum stress can be applied in this direction, right? So that's the ultimate strength of the composite in the transverse direction. So this is based on the failure mode of the matrix, right? And to calculate the to find out the ultimate strain of the ultimate strain in the two direction, people commonly use the empirical formula, which is the function of the ultimate strain of the matrix times 1 minus volume fraction of the fiber to 1/3. Right? So this is the empirical formula based on experience and experimental data. Okay? And you can also get this ultimate strain from the mechanism of materials formula, which is calculated based on the ultimate strain of the matrix, the diameter of the fiber, the center to center spacing between fibers. So this is the arrangement of the fiber, right? And the Young's modulus of matrix, Young's modulus of fiber, you can calculate the ultimate strain in the two direction, so that you can use that in this equation to calculate the ultimate stress that can be applied in the one direction, right? Okay, so that is the case for the failure mode A, right? And for the macro-Barkley failure mode, we know we have two cases. One is in the extensional mode. The other one is the macro-Barkley mode, the shell mode. And that is because the adjacent fibers in the composite may buckle independently, or they may buckle in a cooperative manner. So the case B is the case that the fiber buckling independently, right? And this is the case fibers buckle in a cooperative manner. So for the case B, the transverse deformation of the fiber is out of phase relative to each other, right? So it's out of phase relative to each other. The resulting strains in the matrix are predominantly extensional, and that's why this is referred as the extension mode. So this is the case when the interfiber distance is quite large. That means the volume fraction of the fiber is very small. And if you have in the case C, right? If you have a higher volume fraction of the fiber, the transverse deformations of the adjacent fiber are in phase with each other. So the resulting strains in the matrix are predominantly shell strain. So that's why it's called this mode is called a shell mode, right? It depends on the deformation of the matrix. So this is the experimental result. This is SEM. I think this is the SEM image for the two buckling mode, right? So in the A and B case, right? So the distance between those two fibers is around 3D. D is the diameter of the fiber, okay? And the B case distance is 10D. So there's still relatively small distance compared to the diameter of the fiber. So in those two cases, the buckling, the macro buckling is in the shell mode, right? That means the matrix in between will experience the shell deformation, right? Well, if this distance is really large compared to the diameter of the fiber, those macro buckling are not in phase, right? They're pretty much random. So this matrix in between will experience the extension deformation, right? So for the local buckling models for calculating longitudinal compressive strengths, it's based on more advanced topics. So now I just want to show you the final equations for different models. Okay. This is the model. Is called this model is called a Rosen's model. There may be other models out there to um, evaluate the failure mode. Okay, so the ultimate strength of the composite will be the minimum of those two modes. This is also the strength, ultimate strength in two modes, right? So for this extension mode, it's calculated based on the volume fraction of fiber, Young's modules of the matrix and fiber, right? And for the shell mode, it's calculated based on the shell modules of the matrix and volume fraction of the matrix. Okay, so you want to compare if this composite will fail in the shell mode or the extension mode. If this is shell mode, the stress is smaller, that means the composite will fail in this way, right? Otherwise, it will fail in the extension mode. So in this Rosen's model, in the extension mode, right? In the extension mode, the fibers are out of phase, putting the matrix in tension. So the shell cause shell stress in the matrix is due to the in-phase fiber buckling. So this shell mode is because the shell buckling, right? The shell, no, not the shell buckling. The shell mode is because of the shell stress applied in the matrix, right, in between them. So here, this is the shell deformation applied to the matrix. Okay, so this is the model that evaluates whether this composite will fail in the extension mode or the shell mode in the microbuckling. Okay, but still, this model is not perfect. There's a lot of assumptions here, and you may find this model doesn't work really well with the experimental data. There may be other models there for more precise prediction. So for this model, it assumes that composite, they assume the composite as 2D. So it gives the prediction for extension mode or shell mode failure. Although the shell strength is less than extensional strength, it's still significantly greater than the experimental data. It's based on the ideal assumptions. But it's a great way to predict whether you will have the shell fiber macrobuckling or extensional fiber macrobuckling. And the third, the last failure mode is called the shell stress failure of fibers. And in this way, a unidirectional composite may fail due to direct shell failure of fibers. So in this case, the rule mixtures give the shell strength of the unidirectional composite. Right? You can calculate the shell strength of the composite in terms of the shell strength of the fiber and shell strength of the matrix, right? So in this way, in order to have the shell stress failure, you want to have both fiber and matrix fail, right? So here you have ultimate strength of the fiber and ultimate shell strength of the matrix. you can therefore you can calculate the shell strength, ultimate shell strength of the composite based on the rule mixture. So the maximum shell stress in the laminar under the longitudinal direction compressive load is happened at 45 degrees, so it's around the ultimate strength over 2, right? So that will contribute to the shell stress in the composite. So that means you have the shell stress in this way, right? In the one direction, compressive shell stress in one direction. However, that contribution to the shell stress tau 1, 2 is only half of the normal compressive stress. So therefore, you can get the relation between the normal stress, right, the normal compressive stress in terms of shell stress of fiber and shell stress of the matrix. So this is when you have the shell stress failure, right? You can calculate the ultimate stress in this way. You can also use this. You can also measure this compressive strength, right? Experimentally. So this is a typical longitudinal compressive stress versus strain curve. It's pretty much a linear curve before failure. You can also this is some examples for the experimental strengths and compare with these equations calculated based on the models that we developed, right? We're using. So you see there's a big difference between the experimental strength and this model predicted strength. Usually for the experiment, for this experimental strength is much less than the theoretical strength, right? Because the composite is not perfect, right? So there are a lot of factors that contribute to this this big error. For irregular spacing of fibers, that will cause premature failure in the matrix-rich area, right? You know, if you don't have a good dispersion of the fibers in the matrix, you will have the matrix-rich area, and that matrix-rich area will be the failure point, right? And you have a less than perfect bonding between the fibers and the matrix. So if the bonding is not good between those two, that's the failure point, right? And you may have a poor alignment of fibers. In that way, in that case, that you will not have a strong reinforcement in the axial direction, in the longitudinal direction. And also, those models didn't account for the Boson ratio mismatch between the fibers and the matrix, right? And it's also not accounting for the transversely isotropic nature of the fibers. Right, so that's it for today's lecture. It's a little bit more and than the usual lecture, and we covered a little bit more. We covered some of the failure modes, which is usually covered in chapter, I think, chapter 12, right? So it's a little bit more than the normal macro mechanics. Okay, so I hope you guys can after watching this video, you can take your time to read the book, right? And then let's work on the homework.
Yes, but not the way you do. It's all ones and zeros to me.
Okay, that's the stupid audio. It's a Cortana. The Cortana by Microsoft. It's really dumb. Okay. All right, so that's it. Stay safe, and I see you during the next lecture. Okay. Oh, and also we have online office hour meeting this afternoon. Right. I hope you guys can join it. Thanks.